Hello, I hope you guys are having a fantastic day at whatever time you're watching this. My name is James Mosley and I'm part of Teammate, and today we will be presenting to you guys the Reverse UML R class project, converting code into UML diagrams. Now for our team members and roles. For the front end team, we had three people: me, James Mosley, Dominic, and Jared. For the back end team, we had Matt, Richard, and Joe. And then for our Scrum team, we had Matt be our product owner, and we had Joe as our Scrum master. Now I'm going to go into the start of our phase one, our project development process. Now, our promise statement. In our current day society, modern society, technology is always becoming more prevalent. It's being integrated into more and more daily tasks and the daily things we do. It's there to help make tasks more simplified, easier, quicker, faster, more adaptable. There is smart technology out there that adapts to the person using it, which helps save on both time and resources. Where depending on your habits and so on and so forth, it modifies itself to that. Technology is always increasing. It is always a need to make a task more efficient, more easier, quicker, and it's always being sought after to increase this process. It's started to seem outdated to take a pencil and pen and a piece of paper to create regular diagrams. Even though this could be useful for doing rough sketches and so on and so forth, just to jot something down, that is useful. When you're actually creating a diagram to use for a full scale project, when you're in an actual workplace or even for a class project such as this, you don't want to hand draw it. You want to use a software. Now there is software out there where you can create these diagrams with, such as Malio 4.0, StarUML, and Lucidchart. However, you still are wasting time actually going out your way to create the diagram itself. There's not really that much technology out there where you can really take source code itself, put it into a software, and then have that software generate a UML diagram. As a developer, developers nowadays, or as they're in a fast-paced environment, time is money, so on and so forth. Um, they need a way where they can take the source code, in our case being Java, from an object-oriented language, and be able to put that in a software and then have a UML diagram displayed for that to save them both time and money and resources. Now for our objectives and our functional requirements. As for the system itself, it shall be able to identify and parse the user input to construct and print a UML diagram. For the user should be able to enter source code, primarily being from Java and other object-oriented languages. And as well as this, the user shall be able to generate a UML class diagram from the code that was inputted into the system. Now for our non-functional requirements. For the first one, we have reliability. Code shall be inputted by users and shall remain unmodified by our system, the reverse UML. For maintainability, the system shall be lightweight while maintaining full functionality. For performance, the system shall handle large amounts of code inputted. And for reliability, the system shall return a correct UML diagram with complete descriptions and relationships between the classes. Now for our target environment. Users shall be able to access the service using web browsers such as Chrome and Firefox, the typical average day web browsers, while using the operating software such as Windows 10 and Mac. And as long as the web browser can support an object-oriented language such as Java, JavaScript, HTML5, and CSS, everything should work fine when running on software. And now I'm going to pass on the presentation to my next team member.
Hello everyone, my name's Joel Mozo. I'm part of Team 8. I'm going to talk through these next few slides, starting with technologies and tools that we use to help develop reverse UML. Starting with the front end, we have React. which uses JavaScript, HTML, and CSS to help us develop the front end and web app that you see in the demo. In the back end, we use Spring Boot, which is a Java tool, as well as Gradle, which is our automated build tool to actually build the application. Our development tools, we used Visual Studio Code and Star UML along the process. We also have collaboration tools. We use Discord primarily for communication. We use Google Drive for document sharing and editing whenever we work together. And we also used GitHub as our code repository. Moving on, we have Scrum. Why Scrum? Well, it is a development process that involves a project work being divided up over the course of multiple sprints or stretch goals. This allows the group to measure our progress for the application and have a schedule to deliver a finished project on time. Throughout all the phases that we were given, we broke each phase up into sprints. That way we can manage it better and make sure that we were accomplishing all the tasks within a sprint for the week or 2 weeks that we gave ourselves to make sure every feature that we wanted was implemented. Moving on, like a real product or application being developed, we'll show the class and the professor demos and prototypes of our design, just like a real world project, to ensure both confidence and progress. Many of our group members have used Scrum in the past in other classes and projects, so the process is familiar to the group and there won't be a learning curve with how it is structured. It made the most sense for us because it's one that we all agreed with, and like I said, we're familiar with it, and it's the easiest to follow along with a project that we're given a short amount of time to work on. Moving on, we're going to talk about the risk analysis that we had along this project. The first risk that we identified was scheduling. We made this a medium priority risk. The main risk factor being that team members have other classes and commitments to attend to, which can lead to a lack of work production in this project. We knew that everyone had their own schedules, whether it be class, work, or just any other activities they had going on in their life. So we made this a medium priority. The probability of us not being able to meet as a group when we schedule it was about 30%. A little bit higher than we would like it to be, but we understand that with everything being completely online, this was going to be a problem. The main impact is that as each member has their part of the project to work on, it can cause delays for when they finish the part, which can lead to delays in other parts of the project as well. So starting from the very top all the way down to our application, we had to build some things first, and if we didn't have that ready, we couldn't continue with the rest of the features we wanted to add. Our monitoring approach was to have weekly meetings every Wednesday to ensure that everyone is on track with their part, which worked out great for us. And our contingency plan was pairing group members together, so if one person couldn't work on it, the other person can pick up where they left off and finish that sprint on time. The next risk factor we had was our compatible code, which was a high priority risk for us because code can come in different versions and may not be compatible with the code that's already been pushed to GitHub, which would lead to our application not being able to run at all. The probability of this was about 20%. The impact was that if compatible code is pushed to GitHub, this can cause the overall code for the project to run with errors. Basically, if someone was using a different version of Java, maybe they weren't completely up to date or they had a more updated version, if they tried to push their code to GitHub and our application didn't support that version or our tools didn't support that version, our application would break. So again, our monitoring approach was just to go over and make sure that each week we're all using the same version for the entire project, and our contingency plan was to make sure that we used version control within GitHub and downloaded the weekly versions from there. That way the source code on the local computer matched what we pushed to our org. The next risk was task management, which we had at a medium priority. And the risk factor is that team members may get too engrossed with their current task and spend more time than necessary on one specific task. This was a higher probability at 40%, and this could impact the overall project to be delayed or not even to be completed. So once again, our monitoring approach was to make sure during the weekly meetings everyone was on track, and if someone needed help, we would reach out and help when they needed it. And our contingency plan was to delegate another team member, kind of like pairing, just to make sure that everyone is working through at the same pace and no one's getting hung up on. Next, we have the new technology integration, which was a low priority risk for us. And the risk factor was, as the project progresses, team members may encounter new software, code, or technology that they have never used before and have no understanding of how to use it. The probability of this was 80. And the impact is that if a team member were to encounter a new technology, time would be wasting attempts to learn instead of working. This happened quite a bit in our project as we were implementing a lot of new tools that not everyone was familiar with. So we did have a slight delay during the initial sprints that we had set for ourselves, but we were able to work through it during the weekly meetings, once again, which was our monitoring approach. Our contingency plan was to help create channels in the Discord to enable team members to reach out when they needed help, and we can just all respond on there and teach each other and learn along the way on how to use the technology that we had implemented. Thank you, and now I'm going to pass it on to our next team.
Hi, I'm Jared, and I'm going to be talking about phase 2 and 3 of our project, which was our design and implementation phase. So one of the first things we had to do was we had to create a use case diagram for our project, which we titled Reverse UML. So we have 3 components right here: our user, the parser, and our UML generator. So the user is able to interact with all 5 of our cases right here. So they have the choice between uploading a single file or multiple files. The parser then converts the code from those files, and then our UML generator generates a diagram from that converted code and then displays the diagram for the user to download. The user is able to interact with all 5 of these, whereas the parser interacts with the uploaded file or files and then converts the code, while the UML generator converts the code into a diagram and then displays it for download. So in our domain class diagram, we have our developer or user, which has our file right here, our string path. They upload it to the parser. The parser then must verify that this code is in a language that it understands. If that is deemed true, then it will create a component, giving it a name, attribute, and method, which will then go to the UML generator, which then generates the UML diagram. So if we look at our design class diagram, our title being Reverse UML, our developer has this code right here. This goes to the parser right here, which then must check its database if the language it matches, if it's in there. So if the language isn't in there, then it won't run. But if it is in the database, then it is able to, like I said before, create a component which the generator can then use to display and make a diagram, which is then available for download. So if we're uploading a single file, we have like the normal little scenario where the user, they want to have their code uploaded and changed into a diagram. They upload. The precondition is that it must be, like I said earlier, a language that the system can understand. You can't put, if it's an object-oriented system, then you can't put in a random computer language like binary or Visual Basic. It needs to be one that's actually in there, like Java, Ruby, stuff that has actually been defined as it is in this database. The main success is that we want them to be able to upload their code and get a diagram that is correct for them. So uploading the code should take no longer than a minute, and then the frequency should be continuous. So as you can see from the sequence diagram here, the developer or the user will submit their code to the parser. The parser then minifies the code and then it uploads it to the language definition right here. And then once it has been converted there's a response, and then in step 5 it actually gets displayed to the parser, and then it gets displayed back to the developer or the user who actually submitted the code originally. Now for uploading multiple files, it's almost the exact same scenario. Person wants, in this case, they want multiple little pieces of their code uploaded and changed into UML, so we have the same thing. It must be a language that the computer can actually understand. Like I said before, if you're doing object-oriented, you can't do something that isn't object-oriented, it just won't work. And then the idea is that we want the files to be minified on the front end, and then once they are sent to the back end, they're then converted and changed into the diagram and displayed for the user to both view and download. Now, like we said before, when it comes to uploading multiple files, again, it shouldn't take that long, but it might be a little bit more time given that it's multiple files instead of just a single one. And then if we look at our sequence diagram right here, basically it's almost identical to the single file, except when you submit your code, you then just keep doing this loop over and over again. So you can keep submitting your code, it will be continuously minified and then uploaded to the language definition. This responds right here, parser then and displays the response for itself, and then it gets displayed back to the developer, where once again they can download it or view it.
Okay, this is Dominic Pizzoli from Group 8. I'm going to just talk about a couple of our use cases here and then demo a little bit of the code. So the first one here we have is the running of the code conversion. The scope is reverse UML. Primary actor is just our backend system. Stakeholders and people of interest is a developer who wants their code to be turned into a readable UML diagram. Preconditions, the code that's being converted must already be coming from an object programming language, object-oriented. The success guarantee is that the code is converted into a format that can be transformed into a UML model. The main success scenario, the code that is inputted is successfully uploaded. The uploaded code gets verified by our language library. The code is parsed, and then the system responds by displaying the completed UML diagram. Some extensions. The inputted code is not in a language recognized by the application, so the code upload fails. Code is not converted because the system does not recognize the code. The developer can try again by re-uploading an approved language, or there is any error in the code submitting, resulting in a broken diagram. Again, though, they can retry by uploading the correct code. System requirements, there's none. Some technology and data variations, there's none. Just needs to be an object-oriented programming language. The frequency of occurrence for this is every time the application is run. And open issues, we have none. And this is the diagram for this here. So you have code parser, and language definition is the 3 lifelines. The code is sent from the code to the code parser. It's received. The code parser then sends to the language definition library, verifying the language of the code. The language definition library responds, and the code parser then parses to the code to a UML, and the person is able to view the UML diagram. So the second one here is view diagram use case. Again, the scope is reverse UML. Primary actor is developer. Stakeholders and interests is a developer who wants to be able to see their converted code before they choose to download it. Preconditions, the code uploaded must be from an object-oriented programming language. The code must run through the conversion, and the code will need to have successfully been converted for a preview to be available. The success guarantee is the developer will be able to see their code created into a UML diagram and review it. So the main success scenario is the code is inputted successfully and uploaded. The uploaded code gets converted to nom-nomal. The UML diagram receives this converted code. Diagram gets created, and the system responds by displaying the completed diagram. Some extensions. The inputted code is not in a language recognized by the application, so the code upload fails, and the backend will refuse the code and return an error message. Some special requirements. Obviously need an internet connection to access the application, and it runs on multiple browsers. Again, some technology and data variations. It needs to be an object-oriented language. Frequency of occurrence is every time a new piece of code is converted, and nothing miscellaneous here. So this is a diagram. You have the developer, the model view, and the UML diagram as your 3 lifelines. So the developer sends the code to the model view. It receives the code, converts the code to nom-nomal. Then the UML diagram receives the code, draws a diagram, and responds to the developer with the model itself. The final use case we have here is downloading the diagram. Scope again is reverse UML. Primary actor again is developer. Stakeholders and interests is a developer who wants to download the UML diagram that was generated by the application. Preconditions is the code that was created must have come from an object-oriented programming language, and that the conversion was successful. Success guarantee is the developer will have a version of the diagram modified into an image file and be able to download it to their device. So the main success scenario is the UML diagram is displayed and the developer can view it. The developer then clicks the download button to begin downloading the UML diagram to their computer. The system responds with a message displaying the progress, and the UML diagram image is successfully downloaded when the system responds with download complete. Some extensions, connection failure while using the application, and the page needs to refresh. So download fail. The download button will queue the download. If an error occurs, the developer can refresh the page to retry. Special requirements, must be able to display a website on different browsers. Technology and data variations, again, must come from an object-oriented programming language. And the frequency of occurrence for this one is only when the user decides to download the diagram by selecting the button. So the sequence diagram for this one here, we have developer, package, and download as the 3 lifelines. The developer requests download by selecting the button. So the package receives it, verifies the model, then it sends to download the package diagram, and download responds with download diagram completing. So that's it for that there. And I'm just going to demo a little bit of the code from the file uploader we have on the application. So this is pretty simple. It's just a form, and inside the form, you have a input of type file, and it's multiple, so it allows you to upload multiple files at once. You have an on change and you have an on submit functions. So if you look here, you have on submit, handle submit. If we come up here, you can see function handle submit. And what it does is it loops through the files. That way it submits each one of them. And the location that it sends the files to is the backend here, where it is then able to be parsed. And I believe that is really it for this here.
I'm going to be going over the backend code and explain how it functions. So the backend is built with Gradle, which is a build automation tool. It uses the Spring Boot framework, which handles the web server and all of the web requests for us. We use the Antler library for parsing the files that get uploaded, and from there we generate our own models to store information about classes, their relations, and their attributes and methods. These models are then what get returned to the front end, which then uses them to build the UML diagrams. So first up we have the controller class. This is where a request from the front end first enters the backend. There are 2 endpoints created here, the single and the multiple endpoint. The single endpoint only accepts 1 file, where the multiple endpoint can accept any amount of files. They both return a list of custom class, which is the model we made to store information about an OOP class. Both of these endpoints take the files that were uploaded by the front end and pass them over to the file service, which handles the parsing of them. It calls the generate class from file method here. So now I'm going to go over to the file service right here. The main method here is the generate classes from file, which is what the controller calls. It first gets the file type right here from the file that was passed to it through this method right here. Then, based on the file type returned, it goes to this switch statement here. We only had time to implement Java parsing, but if we wanted to parse other languages, like say JS, which we were planning on doing right here, we could just add another case statement. So in the Java portion, it uses a bunch of classes from the Antler library to make the lexer, parser, parse tree walker, and whatnot. In addition to the Antler classes that we use here, we also use the Java listener class, which we wrote, to listen to the parse tree as it's walked and make actions depending on what is encountered. After the parse tree has been fully explored, a list of custom classes right here is retrieved from the listener, and that's passed back to the controller down here. So now I'm going to go to the Java listener class, which is the biggest class that we wrote for our backend. This extends the Java 8 base listener interface, which is a class generated from the Antler library for parsing Java. I'll pop into it really quick. It's very long and has a lot of different methods that can be overridden, but we only used the ones that we needed here. So this Java listener uses a stack here to keep track of which class it is currently in. So when it comes across a method or a field, it knows which class that they belong to. We override only the methods that we needed for this, which can all be found in the Java 8 base listener class. These are called by the parse tree walker when it encounters a node of the corresponding type. So for example, interclass declaration is called when a class declaration is entered from the parse tree walker, and it's passed the context, which is another class from Antler. So within these classes, we create one of our custom models to store information about that node, and then set the information accordingly. So for the class, we set the name right here. we get if it has a parent class, if it has any interfaces that it extends, and then all of the modifiers here that it gets, and has a switch case based on what the modifier is, and then it sets the information in our custom class accordingly. If the node that is encountered as a class or an interface, it's pushed to the stack, so that when it gets to a field or a method, like in these two methods, it knows what class it's in. And then at the bottom here, when we exit the class or exit interface, the top of the stack is popped. So now I'm going to go over all of our custom models, which are used to store the information about different parts of an object-oriented class. We first have the custom class, which has a few attributes here which describe the class, and then has attributes and methods. I'll go over the attribute next. It's pretty small, just has these attributes within it. And then the method class is this, which has a list of arguments, which is another model we made, which is just this. And that is everything for the backend portion of our project.
Hi, my name is Matthew Neighbor, and I'm the project owner for this project. The project is called Object-Oriented Parsing Tool, and it allows us to download multiple files or one file and understand the UML diagram. To quickly demo the project, I'll just select these files, choose Upload, and then hit Submit. I was personally responsible for handling the displaying of the UML diagram itself. As you can see, there is a parent class animal with subclasses cat and dog, as well as variables with variable types and methods with return types. I worked on the model view class, which has two methods, convert class and the model view constructor. This first method, convert classes, takes on a JSON file, JSON object, and parses it from the ANTLR code into a language that NomNomal will understand. Once that is done, it is then displayed and drawn on the screen with this method. For our references slide, I'd like to draw some attention to our ANTLR library has been extremely helpful for our backend file parsing. We also used a lot of Java references, trying to understand how parsing works and how to upload a file. We utilize Spring Boot in our application. And we had one of our programmers, Dominic, learning that as well. And on our final slide, I'd like to draw your attention to our NomNomal reference. We use this library to visualize our UML diagram. Thank you for watching our presentation.